Hello.
Hi.
Hi, Andrea.
Hi, Valerie. Nice to see you. I'll be chairing this session. I'm sorry I couldn't join the previous lectures, so I missed the QR code. Is it you always a step ahead? I'm impressed. Very nice.
You can still participate this lecture with the QR code.
Now I
New
check,
code, new lecture.
I don't know what happens, but I verify it immediately. Ah, wow. Very impressive, very impressive. Okay. It is time to start if you're ready. The recording has started already. So if you want, we can start. Valerie, you have the honor of closing the school with the last lecture, please.
Okay, thanks a lot. And yeah, again, it's a pleasure to be here. I'm very impressed how many people are still here in the Zoom room, given the very ambitious program you've been through so far. Yeah, so today I want to talk a bit about cosmological sources of gravitational waves, and that ties into the question about how we can use gravitational waves to actually probe BSM physics. And I'll talk a bit kind of about, I think, the big opportunities that there are in this field, but also the difficulties. So just to recap, kind of the main take-home message of last lecture was that we're, in particular for cosmology, we're interested in the so-called stochastic gravitational wave background, which is a superposition of gravitational waves arriving from all different directions with different frequencies, kind of a confused background noise in gravitational waves. And there will be, we expect there to be both an astrophysical and a cosmological component to that. The key computation that we did last time was to actually compute the energy density in gravitational waves, which we found that we can get it by taking the 2-point function of the time derivative of two gravitational waves. And we saw that kind of factoring in that we're looking at cosmological sources, so that there is an expansion of the universe, that this is typically always a convolution of some primordial power spectrum, which kind of contains the information of the source, and some transfer function, which contains the expansion of the universe. And here I've set the scale factor today to 1, right? So instead of then, normally you would have the full ratio here. And then when we're actually talking about predicting some sort of gravitational wave spectra, then the quantity that we'll be interested in also in these lectures is capital omega GW, which is essentially just looking at this energy density per logarithmic frequency bin, in normalizing it to the critical density so that we have a dimensionless quantity. So now we want to talk about first a little bit general, what sort of kind of energy scales we think we can probe with gravitational waves, how we translate between energy scales in the universe, frequencies today, what sort of constraints there already are, and then we'll talk about some popular cosmological sources. So I invite you again to go to this QR code or just type this link. And I just want you to make a guess what energy scales you think that LIGO can probe, right? So LIGO is an existing gravitational wave detector in the US. And if we now want to do particle physics with that, what energy scale do you think we can get up to? Obviously, this is very rough, right? I mean, as you will see, there's some caveats in the argument. But what sort of energy scales do you think we can probe? For reference, the LHC, right? So the strongest collider that we have on Earth is about 10 TeV. Just, you don't have to know the answer, right? Just make a guess, just to then kind of see if then we do the computation, we'll see how it contrasts with your expectations. So essentially what we want to know is the characteristic frequency of relic gravitational waves. So relic, I mean here that we have some cosmological event, and we see essentially the afterglow of this event and want to draw our conclusions from that. So to do so, we will need to first take into account redshift. So if we are observing a gravitational wave today at some frequency of f0, right? So this is the observed frequency. And then this corresponds to some gravitational wave sourced at some early time, say tau star, with some frequency f star, which is related to the frequency we observe it by a simple redshift relation, a of tau 0, right? So this is the emitted frequency. So that is one observation, one argument we will need. The other argument we will need is that if we look at a cosmological source, then the rough expectation will be that kind of the relevant energy scale, which determines kind of the relevant length scale of the process, is typically the Hubble scale. So the horizon scale at that time. That's not exact, right? So we'll introduce a fudge factor, but we're going to parameterize this frequency at which the gravitational wave is emitted, which essentially corresponds roughly to the size of the object which is emitting gravitational waves, as some epsilon, which will always be smaller than 1 for causality, times the Hubble horizon at that time. And then -1 because it's a frequency, and this is the length scale. And that's actually all we need. That's the assumption that go in here. And now we can evaluate this in, let's just for simplicity take the radiation area, because this is where most of the interesting cosmology happens, and actually is kind of what most of cosmological history is actually about. So we can, in this era, we can write that the Hubble parameter is given by Hubble. This is just a Friedmann equation, right? That the Hubble parameter squared is temperature to the 4, it's energy density, and then we have m star squared here, where m star squared, this is essentially the Planck mass plus some factors of pi and degrees of freedom. So this is roughly something like 10 to the 17 GeV. And then we will need that during radiation domination, the scale factor goes as 1 over temperature. And that's all you need, right? So now you can compute with this information, you can now translate, you can plug this in here, right? And then you have the emitted frequency, and then you plug it in here, you get the observed frequency. And what you find is that the frequency that we observe today is roughly 10 to the -8, epsilon star to the -1, T star normalized here to GeV, times in units of Hertz. So this is the relationship between at what time the frequency, at what time your signal is emitted in units of temperature to the frequency at which you observe it today. Or we can also use the time temperature relation, right? So during radiation, time goes as 1 over temperature squared. So we can also check what sort of time does this correspond to. And here we get 10 to the -22 units of seconds. Again, there's an epsilon star to the -1. And now this would correspond to 1 Hertz over f0, right? So this tells you if you have an event which happens at whatever GeV scales, right, then it would correspond to a frequency roughly of nanohertz. And then you could put the nanohertz in here, right, and then see how that corresponds to time scales. And this is the time we measured since the Big Bang, right? So LIGO, for example, right? LIGO is roughly is a few hertz. So like the time that LIGO probes in its units is 10 to the minus 22 seconds after the Big Bang. So extremely early times. So now to kind of answer the question of the quiz, we need to now specify this epsilon, right? So let's, for simplicity, just take epsilon star equal 1. So really say we have a cosmological event and the relevant length scale is exactly the horizon size. And then we want to, for different gravitational wave experiments, let's have a look at frequency observed today, temperature at which the cosmological event happened. And then, for example, for PTA, these are pulsar timing arrays. They are sensitive at roughly 10 to minus 8 hertz. So this will sense the reference value up here. And we see, okay, so now already my numbers don't quite match, right? But so this should be then roughly 1 GeV here, just simply from this formula. And now you can go to the other gravitational waves experiment. So LISA is at slightly larger frequency. So LISA is about 10 to minus 2 hertz. You plug it into these formulas above, right? And you'll find 10 to the 5 GeV. So there's already higher energies. And then finally, LIGO, we have 10 to the peak sensitivity of LIGO is about 100 hertz. We plug it in these formulas and we get something like 10 to the 9 GeV. So this means that in principle, LIGO can really probe extremely high energies, right? The kind of the typical cosmological event that would show up in LIGO happens at an energy scale of 10 to the 9 GeV, which here, by the way, the majority vote here got it right. But there's a caveat, right? And that is that the further, like here from this little table, you would conclude that kind of the higher the frequency of the detector, the better it is for measuring cosmological sources. However, there's an additional effect, right? And the additional effect is that the higher, we saw the other day that for subhorizon gravitational waves, the amplitude decays as 1 over scale factor. So that means if you have some event which sources gravitational waves of a given strength, the further that event is in the past, the more the gravitational wave is redshifted, or well, not redshift, but like maybe diluted if you want. The amplitude decays when we detect it today. So that makes it very challenging to actually see these things, right? So, but if you had, so this table is essentially telling you if you had an arbitrary sensitive detector at this frequency, then this is the energy scale you could get to. But in practice, we are of course limited by the finite sensitivity of the detectors. But still, kind of there's the comment to make that in principle, if you could build a good enough detector, we have access to very high energy scales. Are there any questions on that?
Doesn't seem so.
Okay. Then
yes, one.
Yeah. Manuel?
Hello, thank you for taking my question. How far away is the sensitivity of the detectors we have right now from the needed sensitivity?
So that depends. We'll go through a few examples. It depends on the strength of your source. Right? If you had an arbitrary, if you had an extremely strong source, then you could even see it with the current detectors. But yeah, it's both factors play into the game. But we'll see later on. We'll see for a couple of examples. We see how far away we are.
Thank you.
Another one.
Yeah. Hello.
Yeah.
Can you hear me?
Yeah.
Yeah. So can you please repeat once more? So why did you take epsilon equal to 1?
It's just an example. So the general statement is that epsilon star should always be smaller than 1, right? Because this is causality. Like the event should not be bigger than the Hubble horizon. Otherwise, we also don't have propagating gravitational waves, as we saw. And then it depends on the type of event that you have. So for a lot of cosmological events, the Hubble parameter at that time sets the relevant scale. And then you have epsilon close to 1. But we will also see examples where epsilon can be something like 10 to minus 3, 10 to minus 4. And then you have to kind of this is why I left it inside these formulas here, right? And then you need to kind of accordingly shift your frequency range a bit.
Okay, thank you.
Okay, so then let's move on. And the last thing I want to do before talking about concrete sources is tell you about a general constraint, which comes from cosmology and applies to all kind of models of cosmological gravitational wave sources that you might want to construct. And these are constraints from BBN and CMB. And because the reason this is important, that as soon as you build a detector, which is kind of more sensitive than these cosmological constraints, you're essentially in discovery space. So then for sure, somebody can build you a model that you can actually see or test. But of course, as long as you're only probing a regime that is already ruled out from cosmology, then there's little hope of actually seeing a signal. So again, here I have a little quiz for you. So here's again so same link. You should see the next question. So this constraint from CMB and BBN will tell us something about the amount of gravitational wave energy density that we can have in the universe. So I'm quoting here numbers, which is essentially the amount of how much, there's a constraint from BBN and CMB, which tells us how much energy density can there be in gravitational waves total, compared to the energy density in radiation, meaning the energy density essentially in photons, essentially photons and some neutrinos. So how much energy density do you think there can be in gravitational waves? Okay, there's a tight race between 10 to minus 3 and 10 to minus 10. Okay, so let's compute the answer. Well, I want to spoil all of this. Yeah. Okay, so the constraint on BBN and CMB is essentially a constraint on what we call extra radiation, where extra means anything beyond the standard model. And the way this is phrased is that we say that after, in the cosmological history, after the coupling of the electrons, we can express the total radiation energy density of the universe as pi squared over 30. So this is just the usual thermodynamic factor. And then this will go as T to the 4. And this prefactor here counts the degrees of freedom. So we have 2 degrees of freedom from the photon. And then we have the contribution from the neutrinos, which is parameterized in this way. So 7 over 4 n effective 4 over 11 to the 4/3. So the 7 over 4 comes from the fact that the fermionic degrees of freedom enter slightly differently than the bosonic degrees of freedom into the energy density. And the 4 over 11 comes from the fact that once the neutrinos decouple from the photon bath, then the E plus, E minus decoupling, so the annihilation of electrons and positrons, reheats only the photon plasma and not the neutrino plasma. And hence this leads to this factor 4 over 11. But at the end, these are, well, more or less order one numbers, right, for cosmologists. And so this delta n effective counts the effective number of degrees of freedom. So the standard model prediction is an effective standard model 3.046. So naively, you would think it should be 3, right, for 3 neutrinos. It's slightly bigger because of the details of the way the neutrino decoupling works. And now, essentially, the way we parameterize any extra radiation is that we say, okay, any extra contribution here we can always write as the n effective of the standard model plus some delta n effective. And this is the bounds are then typically phrased in terms of this delta n effective, but it's really just a bound on the energy density, right? Just kind of phrased in a slightly more complicated way. So then what essentially the CMB and BBN tells us is that the energy density in gravitational waves at any point in time normalized to the energy density in photons. So this should better be smaller than the total energy density in radiation observed. So this is the observable of BBN and CMB, minus the radiation energy density in the standard model, because gravitational waves contribute to the radiation energy density. So even with this, where essentially if this is saturated, it means that there's no extra new physics, which is relativistic, just gravitational waves. So that's a conservative assumption. And so this should then, from this equation here, be smaller than 7/8, 4/11 to the 4/3 delta N effective. And now if you look at kind of constraints, so if you had extra radiation, that would change the expansion history of the universe, and hence you would change the prediction that we have for Big Bang nucleosynthesis and change the predictions that we have for CMB decoupling. And hence we can say that at BBN or CMB decoupling, we can actually measure this number, this delta N effective. And roughly we get that this delta N effective should be smaller than 0.2, roughly. And then this means, if you plug this back in here, what you get is that the energy density in gravitational waves compared to the energy density in photons at the time of BBN or CMB should be smaller than about 10%. And now, if you want to compare it, and now if you want to compare it to energy densities today, then you have to take into account that both the gravitational wave energy density and the photon energy density will redshift. But since they are both radiation, they will actually redshift in the same way. So in fact, the bound on this fraction remains unchanged over cosmological evolution, right? So we can, in fact, have 10% energy density in gravitational waves compared to the photon energy density. So essentially, the correct answer here, right, is the one with the fewest votes, right? We can actually have 10%. But of course, the radiation energy density today is subdominant to the total energy density because in a matter-dominated phase, radiation redshifted faster than matter. So today, we have that the omega gamma, so the energy density in photons, which is defined as rho gamma divided by the total energy density, is about 10 to minus 5. And so the total amount energy density in gravitational waves is this omega gamma. Then we have this, I mean, this is roughly an order 1 factor, right? So then we just have delta N effective times the total energy density. And so this is roughly, this thing here is roughly a factor 10 to minus 6. And so what we conclude is that the gravitational wave energy density today compared to the total energy density is very small, 10 to minus 6. But compared to the photon energy density is actually pretty large. It can be up to 10%. And now if we want to put a bound on this omega GW, then what people, so this is the pretty robust bound. And now what people typically do is they say, we assume a broad spectra, which means that we're assuming that we have that the omega is something like this, right? And that this width in units of ln(f) is roughly order 1, right? And in that case, essentially, because this thing, the rho is the integral over omega d ln(f), right? But if kind of ln(f) is roughly order 1, which is reasonable approximation for several cosmological spectra, then this actually translates really to a bound on the amplitude of the spectra, which is of the order of 10 to minus 6. So this is the actual bound, right? And this is the bound that people always quote. And so there is a caveat. So the caveat is, so this bound applies for gravitational waves which are already inside the horizon at BBN or TCMB, because we saw that on super horizon scales, gravitational waves don't actually behave like radiation at all, right? They just have a constant amplitude. So this applies for GWs inside horizon at TBBN or CMB. And this is already a pretty serious constraint on quite a few early universe models. Okay, do we have any questions so far? Okay, then let's move on to the sources. No, there's a question. Yes, Gautam?
So what type of models typically violate this?
So I'll show you some examples. So I do, okay, so you can, it really often, it depends on the model parameters, right? But one thing we'll be talking about is cosmic strings. And for cosmic strings, it is simplest model one free parameter, which is essentially the energy density along the cosmic string. And so for models which have a large energy density on the string, this is already excluded.
Okay.
That's one example. But some more exotic inflation models can be excluded. Also with phase transitions, you can actually, in principle, you can get values which are this large. So typically it doesn't exclude the entire model, but typically it excludes some part of the parameter space of the model.
So like a really strongly coupled first order phase transition wouldn't be allowed.
Right.
Okay.
Right. And this thing has a pro and a con. So which is the same thing, right? So and that is that it is not sensitive to frequency, right? Because this is really a bound. We see it more clearly here in this expression. It's really a bound on the integrated quantity, right? So it means that as long as it's only a bound, it's kind of nice because we can apply it over all frequencies, right? And we know that we have no excess radiation anywhere. However, if there were a detection, right? So if we detect that delta N effective is actually with some confidence, I mean, there's already some hints that delta N effective should be a bit bigger than the standard model value, right? Though it's not conclusive. But if we convince ourselves that delta N effective had to be bigger than the standard model value, then that's the end of what you can learn from that, right? It doesn't tell you if it's gravitational waves or some other light species. And it does, even if you convince yourself it should be gravitational waves, then it doesn't tell you at what frequencies are these gravitational waves, right? So you have, from a measurement of delta N effective, you have no way of knowing what is the cosmological model which is generating it.
Right. Okay. So so since this bound isn't really like dependent on characteristic frequency, we talked about it like yesterday that one of the things that people generate through their models would be the characteristic frequency. So like how does that relate to the bound here, or suggest that because this bound isn't related, we have this freedom to do whatever we want along those lines? Or
right. So in fact, right. I mean, so I mentioned yesterday that we typically in cosmology, right, we can get, for example, we talked briefly about preheating, right? And at the preheating, you get very high frequencies, which you cannot probe with any of the detectors that we have so far.
Right.
So this is in fact a very stringent bound on preheating models.
Okay.
So I know several preheating models which are killed by this constraint, and it's also pretty much the only way to probe it. So kind of preheating models which are very violent, right, can violate this bound.
I see. Okay.
But vice versa, as soon as you build any instrument that is better than this bound, right, I'm
then
sure somebody
those
can
models start
construct you a
coming back.
model. Yeah.
Okay, but there is no actual direct relation between this energy density bound and like the frequency that you generate from your model. It's just that the energy scales are just far too high that it just wouldn't work.
Yeah. So this bound really applies. I mean, in particular, this integrated bound, right, really applies across all frequencies. Yeah. But okay, there is a relation. There is a relation. I said that I told you yesterday that if you want to detect gravitational waves at very high frequency, right, they tend to be very energetic, which means that they carry a large amount of energy compared to the displacement that they make, right? And so here we have a bound on the energy, but what the instrument will measure is a displacement. So
Okay.
at high frequency, it becomes increasingly difficult to beat this bound.
Right. So from this, you can sort of say that whatever frequency generated would just be not useful for any detector whatsoever, and that would essentially kill the model.
Say that again.
No, so I'm saying that from sort of the like looking at this bound and sort of the frequency that we generate, like we would probably get a disparity between sort of the distance that a detector can measure, and that disparity would eventually kill the model if it's not possible at all.
Yeah,
Okay.
in some sense, yeah.
Thank you.
Okay, Maria?
Hi. Actually, my question was already kind of answered. I wanted to ask about the phase transitions, if this bound applies to them, but you said already that it applies, right?
Yeah, it applies, and we'll see in a second how yeah, it applies, and we'll see in a second how relevant it is. Yeah.
Okay, thank you.
Okay, so this actually brings me to the slide on the poll. So in the next question, you may take a wild guess what you think is the first stochastic rotational wave background that humankind will detect. You can pick your favorite source. Okay, I see lots of fans of first order phase transitions. Everybody's very optimistic that we'll see it. This is nice. But the Astro is winning over the Cosmo. Okay, so let's look in a bit of detail into some of these sources. And the first one, which I want to briefly cover, is inflation, which we already talked a bit about yesterday. So in inflation, the source of the gravitational waves are the vacuum fluctuations. So the simplest model is just to consider the vacuum fluctuations of single field slow wave inflation. So this, I think most people would agree that this is a source which is there. We are pretty confident that this exists because we have kind of pretty good, well, not evidence, right? But I mean, yeah, pretty good reasons to think that inflation happened, and pretty good reasons to think that it's yeah. And this kind of assuming this single field slow roll is really kind of making the most possible conservative assumption. And then we have a measurement. We have a measurement from CMB data on R, which is a tensor to scalar ratio. So this is this delta t squared that we talked about yesterday, divided by the same quantity for scalar perturbations or temperature perturbations. And this we know is roughly smaller than 0.1. And from that, we have a prediction that in over a wide frequency range, as we saw yesterday, right, this omega GW is constant with power laws at the end, as we discussed yesterday when we have a different equation of state parameter. And from this bound on R, we can get a bound on the amplitude, which is about 10 to the minus 15. And now to put this into some context, the sensitivity of LIGO in terms of omega is 10 to minus 8. And the expected sensitivity of LISA is 10 to minus 15. Sorry, 10 to minus 13. So we don't know if this bound is saturated, right? Because we don't know if R is actually just around the corner. R could also be very small, right? There could be another 6 orders of magnitude suppression here. But even in the most optimistic scenario here, this will be out of reach by a long way for LIGO, right? And even still by 2 orders of magnitude by LISA. So this is something we'll have to leave to the next generation of experiments. But there can still be stuff to detect from inflation. And that is if you have, instead of having this flat spectrum, which we discussed yesterday, if you have more exotic models of inflation, you could have a blue tilted spectrum. Blue tilted means kind of more power at higher frequencies. So this is something I wouldn't bet, personally, I wouldn't bet too much money on, though I have written a couple of papers about it. But kind of every time here you can in principle you can get predictions here. I mean, they depend on the model parameters, right? But you can construct a gravitational wave spectrum which actually gets pretty close to the BBN bound. So every time that, say, LIGO improves the bound, or then when we have LISA, every time that LISA improves the bound, we are rooting out part of the parameter space of these models. Then the next topic was already asked about, first order phase transitions. So if you go by the number of papers on arXiv, right, this is probably the most popular source. And so what is a first order phase transition means? You have some potential of some scalar field. Like, for example, the Higgs field of the standard model. And then this has at zero temperature, this has maybe some potential like this, right? Where it has a true vacuum which is displaced away from the origin. But now at higher temperatures, you will have thermal corrections to this potential, such that at high temperatures, this looks somewhat like this, right? So here temperature is decreasing in this direction. And our first order phase transition means that in order to get from the false vacuum to the true vacuum, the way kind of this change in the power spectrum happens, goes from here to here and so on. There's never a stage where the field can kind of move really smoothly, but it really has to tunnel, right? And if the field has to tunnel like this, then you will essentially form bubbles of false vacuum, bubbles of true vacuums in the overall phase of the false vacuum. And then these bubbles expand, they collide, they do all sorts of violent stuff. Whereas in this, for the electroweak phase transition of the standard model, you have a crossover phase transition, right, which does not have this violent behavior. And then you will correspondingly not get this type of gravitational wave signal. So in the standard model, we have no phase transition which does such a thing. But in kind of extensions of the standard model, this can happen. And hence gravitational waves can be a way to test these type of extensions. So kind of the sources of the gravitational waves here are bubble collisions. So these bubbles are of true vacuum forming in the false vacuum phase. Then once the bubbles are formed, the plasma evolves in a somewhat complicated way, governed by magnetohydrodynamics, and you can have turbulence effects, which are again very violent and source gravitational waves. And then you can have sound waves, which are now propagating through this kind of disturbed plasma, also generating gravitational waves. And so the typical spectrum that you will get, omega as a function of frequency, will be some sort of peaked spectrum, where the frequency here, f peak, is typically something like 10 to the minus 3 hertz t over 100 GeV. So this is in fact precisely the formula that we had above, just that here typically if you compare it, you will see the typical epsilon star here is roughly 10 to minus 3. Which is kind of the typical size of these bubbles in some sense, forming with respect to the Hubble horizon, right? And this you can do to some extent analytically, but you can also do it in numerical simulations. And this is kind of a fun number coincidence, right? Because it tells us that the LISA scales, right, which are in the millihertz regime, are sensitive to the temperatures corresponding to the electroweak phase transition. So if there's some BSM physics which is making the electroweak phase transition very first order, then in principle, this can be checked with gravitational waves. So Lisa will probe the electroweak phase transition. And the amplitude here, right? This can be, so the maximal amplitude, it depends on really on the strength of the phase transition, but it can really be all the way up to the BBN bound, about 10 to minus 6. Again, depending on strength of phase transition. It can also be all the way down to 0 if it's not a first order phase transition. Okay, do we have any more questions at this point? Otherwise, I would say we take a break and then talk about cosmic strings. Yes, there's a question by Gotham. Is that a new hand?
Yeah, it's a new hand.
Please.
So I had some questions regarding the electroweak phase transition in the standard model, right? So why do we not get a first order phase transition?
Well, it's a simply
because I assumed, because is it because it's an avoided level crossing or an actual level crossing?
It's because it's a so-called crossover. So what happens in the standard model? So in the standard model, we know essentially, right, what is the quadratic coupling and what is the quartic coupling describing this potential, because we've measured the Higgs mass essentially.
Right.
And now essentially what happens in the standard model is that the transition here is kind of smooth, goes like this, so that the field can just roll down, right? So there is a phase transition.
Right.
But the field can just roll
from
from one vacuum to the other vacuum classically. There's a classical trajectory connecting the two vacua, and it doesn't need to kind of tunnel to a potential barrier.
Right. So so how would the potential typically will have to look like if you want a tunneling effect?
Here you need this barrier, right? You need that. There's no point in time in temperature where this field can go from here to here without having to cross the barrier. The barrier is what forces you to tunnel.
Okay, so would the same form still remain? Would we still have a quartic and a quadratic coupling?
Yeah, it's really yeah, you can do it with it. It really depends on the magnitude of the two parameters.
Okay, so it would depend on the coupling constants of the quartic and quadratic, and not the actual field. So you wouldn't need like a phi cube field.
Yeah.
Something on it.
Yeah,
okay.
Correct. So you don't have to do a crazy modification of the standard model, but you do have to. Yeah, you do have to do something. Yeah, in particular,
Right,
given the measurements that we have.
Okay, and I'm assuming, like, because I know for like superconducting phase transition, like the mu squared of the quadratic term sort of gives like the bubble correlation length and so on and so forth. So is that how they sort of related, or is it something different?
So I'm not sure, your audio was breaking up a bit, but so the order parameter of this phase transition is essentially the phi, the VEF of this field phi. I'm not sure if that answers your question.
Somewhat. I assume that it would be the mu squared term or the m squared term, depending on how you feel, because in sort of solid state, the only first order phase transition people deal with are superconducting, and that's sort of what goes on over there. So I was wondering, would be similar.
Yeah, it is similar. I mean, that's essentially where the name comes from, right? So the name comes from solid state physics, and so the way to think about it is in terms of this order parameter phi, which kind of tells you go from one phase to where phi is stabilized at 0 to another phase, and where all the particles are, well, in the standard model case, all the particles are massless, right? To some other phase where phi takes a finite value. Okay, Anna.
Okay, and you would need those to be large enough that. Oh, sorry.
Yeah. Sorry.
Great. Sorry, Prof. This is kind of a vague question, but what is it about the first order phase transition that made it so popular? Because it seems like people are quite fond of it, and is that just because Lisa has these sort of sensitivity ranges that make it accessible, or is there something more clearly defined?
Yeah, that is a very good question. Yeah, there's I think some sociological effect going on here. So yeah, so I think one big source of excitement was that Lisa can actually probe the electroweak scale, and that we do something is somehow fishy about the electric weak scale in the standard model, right? We have the fine tuning problem. Our hope is kind of that the Higgs, learning more about the phase transition, learning more about the Higgs will maybe help us understand why, you know, we haven't found supersymmetry, why we haven't found any additional states, why the standard model seems so fine-tuned. So this, I think, is why people are thinking so hard about the electric phase transition, and this is just an orthogonal way to probe it outside of kind of colliders. There was also, I mean, also if another nice thing about if you make the standard model first transition first order is that you could have models of baryogenesis, so models of creating the matter-antimatter symmetry of the universe in a fairly minimal way. So then kind of it would be really a neat story if you had some minimal modification of the standard model, which gives you baryogenesis, and then you could test this in gravitational waves, right? It would be a very, very nice story. It seems to be a bit difficult. It seems kind of the parameter space which actually does the baryogenesis is not identical to the one that you can probe with gravitational waves. But I think this is roughly maybe the reason why people got very much interested in this question. But yeah, I'm not sure why. Yeah, there's also some sociology going on, right? That kind of some people work on it and then other people tag along, and yeah, we'll see. If Lisa detects it, right, I take everything back, and then I'll say this was the right thing to work on.
There's another question by Gautam.
Okay, yeah, just a small one. So since we require a sort of tunneling for the first order phase transitions, especially like baryogenesis models, would that mean that we would look more at like an instanton-based phase transition over a spalaron, because a spalaron would have a smoother roll? Because the instanton process
Yeah. I mean, in some
is
sense,
the
I
one
mean,
that
right.
tunnels.
I mean,
I'm just relating words at this point.
Yeah, though I mean, in both the instanton and the spalaron case, I mean, you do have potential barriers, right? It's just that the spalaron kind of goes over the top, and
yeah, and the instanton tunnels, true. So
right. So I think it's I mean, here this picture is entirely true already. Just I mean, this could be an abelian phase transition, right? And this would already happen. So I think the general statement is simply you need your phase transition to be violent for this to happen, right? Because if it's just kind of a smooth change in some equation of state or in some order parameter, then you have no reason to generate gravitational waves, right? We saw that the gravitational waves are connected to the energy momentum tensor, and in particular to the anisotropic part of the energy momentum tensor. So what you need is a lot of energy, and it leads to be kind of very inhomogeneously distributed, roughly, you know, and that's what sources gravitational waves. So you can also play games with whatever you kind of a super cooled phase transition, right, which violently loses a lot of energy in an instant. You can play different games here, right? But roughly what you need is a lot of energy released in a fairly inhomogeneous way.
okay, and just my last question. So in terms of the three sources that influence this, what are they all equally dominant, or is one thing suppressed over the other in terms of contribution to the entire energy density or frequency? Like would MHD turbulence be more dominant?
Yeah, that I would say is still ongoing research. So it depends.
Okay.
It depends on the parameters also. But I would say that's really still ongoing research. People are
okay. So that would be like a model specific choice.
Yeah.
Okay, great. Thank you.
Okay, so then maybe this is a good point in time to take a short break, and then when we come back, we can talk about cosmic strings.
Okay, great. How long? 5 minutes is okay, Larry?
It's fine for me.
Okay.
Yeah.
Great. And I guess we had 5 minutes, so whenever you want to resume.
Yeah, so let's get started with the third and last topic for today, or example of a source, which are cosmic strings. So, okay, so cosmic strings they're a bit related to the previous point, to the phase transitions, because there's so-called topological defects which are formed in phase transitions in the early universe, right? So again, this is something which is not anything the standard model predicts, but something which you can get quite easily in BSM models. So to explain, let's consider the simplest case of just a U1 phase transition. So we have some scalar potential, very similar to the one that I drew above, which in the high temperature phase, something like this, so field is stabilized at the origin, and then as the temperature decreases, this, and you should think of this as a 3D plot, right? So this is a 3D parabola, and then this kind of, as the temperature decreases, this turns into a Mexican hat type potential. Where now the field value of the vacuum expectation value of this phi field is initially here, right? So it's here in the center, and now it can kind of roll down into the rim of this Mexican hat, and a priori in different parts of space it will roll down to different spots, right? So it will always end up somewhere in this ring, but where exactly it ends up is random. And so if I consider now just in real space, right? So let's consider some plane, I don't know, y and x. And now we consider some patches in this real space where the size of the patch is such that that they're kind of inside of the patch, kind of the fields are in causal relation, and they can kind of uniformly kind of arrange or locally minimize the energy. But kind of this doesn't work globally, right? Because kind of there's only kind of things can only communicate by the finite speed of light at most. So we will have different patches, with like the typical size of this patch is roughly the Hubble horizon. So many different patches all over the universe. And now in every patch, the field will point in some different direction randomly. And now if you look at this, you can have configurations which, where neighboring fields are kind of pointing in similar directions, but you can also have a configuration like here, where you kind of see that the fields are all pointing outwards from this point here. So there's no way that via any infinitesimal transformation, you could align these fields, right? So no matter what you do, you cannot kind of make them all parallel. And this essentially goes under the name of a topological defect. And what I'm doing in a more abstract sense is I'm mapping the vacuum manifold here to real space, to three-dimensional real space. And if this is kind of a non-trivial mapping, then you can get these types of effects. And so if you play the same game, so now I'm just drawing X and Y, right? So if I try to draw this in 3 dimensions, then essentially you can imagine lots of slices, right? The slices all look like this, and now these 2-dimensional areas actually become 3-dimensional boxes. It becomes a bit harder to draw, but essentially this point here in 3-dimensional plane actually becomes a 1-dimensional object, a string, hence the name. And essentially all around this 1-dimensional object, kind of these webs are pointing outwards or inwards. And hence there's kind of no way that you can kind of get rid of this object with infinitesimal transformations. And so on top of this object, the field doesn't know where to point, right? Because there's no way it can align itself. So in the middle of this object, there will be an energy density, which is given here by the height of this kind of Mexican hat potential. So what we will get is a 1-dimensional topological defect in this simple case. This is what we call a cosmic string. And we have an energy which we will call mu, which is essentially v squared. which is the energy per unit length, right? So hence it says dimension 2. It is the energy per unit length along this cosmic string object. So essentially, there's only one free parameter, and the free parameter is just given by the scale of the symmetry breaking. And so I did it here for the simple case of a U1 symmetry. The more general case, if you think about what I said before about mapping the vacuum manifold to real space, so more generally, you get these cosmic strings if and only if you have some breaking of some large group G to some smaller group H, such that the first homotopy group, right? So this is a mathematical object of G divided by H is non-trivial. So this is kind of the mathematical definition. For all practical purposes, it's kind of, for everything we do in this lecture will be enough to just think of a U1 phase transition the way the one that I drew here.
There's a question if you want, Valerie.
Yeah, Yuhi, please.
Hi, sorry, this is regarding the phase transition. So is it possible that higher order phase transitions can be a source of gravitational waves, or is it just the first order that would
It's just first order. So because that's the most violent process. So also in second order phase transitions, it's less violent and hence less gravitational waves. You really need the first order thing.
Okay, thank you.
I see more questions.
Yes.
Max?
Yeah, hi. So my question is about the cosmic string theory. So it looks, so from what you drew and explained, as if the cosmic strings could only live on the Hubble horizon, kind of. But this is not the case, right? It can also be like inside one Hubble patch somewhere, or not.
Yeah. This is just the typical size, right? Because I mean, if you're an observer, right? If you're an observer and you're sitting here, right? Then this would be your Hubble patch. But if you're an observer and you're sitting here, then this would be your Hubble patch, right? And then your string is well within the horizon. So this is just giving a typical length scale, not more than that. Okay, but I mean, if you from our point of view, we could observe cosmic strings. So are you saying that they can only like be right at the Hubble space, Hubble horizon from our point of view? Okay, so we'll see. Okay, so in fact, what I drew here is this is actually not entirely the full story. So the statement is true at late times. So the statement is true that at late times, I'll explain what I mean with late in a second. The expectation is indeed that you cannot have more than one cosmic string per Hubble volume. This is not entirely true at early times, right? Because at early times, kind of it takes, like you form the network, right? It can be a microscopic process. The microscopic process might not yet know how big is the Hubble horizon, right? So initially, you will typically form actually much more strings, right? You will essentially, this domain will be smaller, maybe set by the mass scale associated with this potential. But then as things evolve, you will indeed only get typically one or order one string per Hubble volume.
Okay. Yeah, because I was comparing this thing to the domain worlds, for instance, and I thought that so that there could be several domain worlds in really, from our point of view, in our Hubble patch, but this should be the same story as with cosmic strings, right? Or is there some difference? Yeah, so this is true at formation, right? At formation, you could have more than one, and I'll explain in a second why it comes down to one. This is what when you form the network. In fact, this is initially this is a causal patch, but initially this is not Hubble. Initially, this is typically the mass scale of the string. Yeah. Okay, thank you. Okay, yeah. So let's actually get to that question right away. So this is so here I show you a fancy picture which comes from a real. This is a simulation run by people in the University of Geneva, where they just really kind of they do a simulation where they have a field, right, like this with a potential. They put it on a lattice, on a grid, and they simply evolve the entire. So you can describe this with just a Lagrangian in a kind of a classical field theory, and then they evolve the classical field theory, and then they really kind of see these string objects forming.
But now once we formed the strings, we need to check how the network evolves. And so the key process is that you can have intersections and self-intersections of these cosmic strings. And this generates loops of cosmic strings. So essentially you have one string, for example, which loops back on itself. And then once the string crosses itself, there's essentially an order 1 probability, or it's energetically more favorable for the string to instead go to this configuration where you split off this little loop. And now this little loop can shrink, right? Because the last string kind of was just kind of, there was no way that via infinitesimal transformations, it could radiate away its energy, or it could disappear. But now once you form this loop, the loop can shrink, right? And you can, in principle, by a continuous transformation, get rid of the object. This is why it is energetically favored to form these loops. And once you have these loops, they can emit particles and gravitational wave radiation. So with particles, I mean the particles which are somehow associated to this U1 symmetry. And they can also emit gravitational waves. So you should imagine that you have some loop, and the loop is somehow oscillating around in space, right? And it is emitting all sorts of stuff. And hence it is shrinking and it is losing energy. So then over time, you reach what is referred to as the so-called scaling regime. And this now goes back to Max's question. And this is essentially, you can compute this not precisely, but you can do this pretty well analytically. So the scaling regime arises essentially when if you can write down an action for these loops, and you can evolve in time. And the evolution is a fixed point, a mathematical fixed point, which just tends to head to. And in this fixed point, you find that the energy density of cosmic strings compared to the total energy of the universe is pretty much constant. And the normalization is such that you have order 1 cosmic string per Hubble volume. So indeed, kind of initially the scale is smaller, right? So maybe I shouldn't write the h here. But then once you factor in the evolution of the network, you evolve towards a situation where you only have order 1 long string per Hubble volume, but you have kind of a bunch of loops which are happily emitting gravitational waves and particles. And so the difference to domain walls and monopoles, and essentially all other topological defects, is that you can form these guys, right? And they are topologically stable, but they kind of tend to a solution where they make up a fraction of the energy density of the universe, but they don't come to dominate the energy density of the universe. So the existence of these objects is perfectly compatible with all kind of the measurements of cosmology that we have, right? This is different to, for example, monopoles, which are one-dimensional, zero-dimensional topological defects, which if we form them, they would kind of tend to want to dominate the energy density of the universe, and then that would be in contradiction to our observations. Any more questions about this? Yes, Gotham, please.
As this sort of system evolves and like you form loops and stuff, would there also be domain wall annihilations that sort of give rise to these gravitational wave spectra? Or
but you're asking about domain walls? Was that it? Did I hear correctly?
Yeah. Like, would there be domain wall annihilations as the system evolves?
No, there's no domain walls here. Like if you start with this type of story, right, a U1 breaking, there's no domain walls. There's just cosmic strings. That's the only topological defect that you form.
Okay, but if you had, like, I don't know, a higher order, like
if you would break instead of a U1 symmetry, if you break a Z2 symmetry,
okay,
right,
yeah,
then you would form domain walls. But then you would not have cosmic strings. You would just have domain walls. And then you would normally be in trouble, because domain walls also have this property that they come to dominate the energy density of the universe.
I see. Okay, so
usually that kills your model.
right, but but since you mentioned sort of the Z2 group, so would domain wall phase transitions be something that people use in BSM dark matter models, because I see a lot of them on arXiv these days?
Well, as I said, as soon as you form domain walls, you're usually pretty toast, because you would simply predict that you have a domain wall dominated universe, which is clearly not the case.
I see. Okay, great. Thank you.
Okay, so now, of course, so this is kind of the basic story about cosmic strings. Now we are interested, of course, in this gravitational wave emission, right? Because that's the thing that this lecture is about. So what is actually the gravitational wave signal? And you can compute the gravitational wave signal in this model essentially by, so what you need is the power spectrum of a single loop. So this is the power spectrum of a single loop. And this index n here indicates the harmonic. So you can imagine really that the loops are oscillating, right? And they can oscillate in different harmonic bands. And so we'll have the sum over all harmonics to get the final story. And then also we need to know how many loops do we have. So this is the Cn of f. So this tells us number of loops emitting gravitational waves. Which with these gravitational waves are observed at a frequency f, which is the frequency over here at time t, which is the time over here, right? So then, of course, you have to factor in the redshift, right? So this means that kind of you have the different redshifts. This will be different size loops, which are now emitting, such that then after redshifting, you have the given frequency that you are interested in. So this thing, and yeah, so what you need to compute is these two objects, right? And this Cn object here, what does it depend on? So again, okay, you have some prefactor, but then the important part is you have to do a redshift integral, right? Because as I say, we're interested in loops that emit gravitational waves such that the frequency today is f, right? But that means that they can emit at different frequencies over the evolution of the universe. So we need the number density of loops which have a given length, which depends on redshift, and a given time, which trivially depends on redshift. And we have depends on a cosmological history, which enters with the Hubble parameter, and then 1 plus redshift to the power 6. So this thing here, this curly n, is number of loops of length L at time t. And then if you have a loop of length L, it's directly related to the frequency simply by as soon as you know the harmonic. So the length is related to the emitted frequency in this way. And now you do the redshift integral, and this is how you ensure that you really get all contributions in which today have a given frequency. So the reason is, okay, so the reason I wanted to just sketch to you where this comes from is because I wanted to tell you what we know and what we don't know. So essentially, one thing you need to know is this number density, right? This is one ingredient. And so this number density is this is the number density of loops and the properties of loops. And this, to some degree, you can determine analytically. And then people have also gone to great effort and run huge numerical simulations to get a handle on these number densities. And there's some sort of, and this is really still an active topic of research, right? There's some convergence, I would say, in the process, but there also are still groups which completely disagree on this, right? So this is one big challenge. This is a purely theoretical exercise to understand really what is the prediction. Like the model is very clear, right? The model is just this. We can write down the Lagrangian in a single line. The question is kind of now to predict this number density. And the other thing that you need to predict is the power spectrum of a single loop. And the power spectrum of a single loop depends a bit on the substructure of that loop. It depends a bit if the loop is completely smooth or if maybe the loop is more wiggly. So there's also some uncertainties there. But yeah, so just to keep in mind, right? Because essentially all results I'll be showing will be subject to these uncertainties, and this is a very active topic of research to try and get these under control. So then, but if you have this, right, and then you can take these numerical simulations, you can plug in a number density, and then you can actually compute this omega GW, which was related, just to recall, this is 1 over rho C d rho GW d ln f, right? So if you have this quantity up here, you can get this quantity down here. And then what we get typically is, so this is now as a function of frequency, and to give some orientation, so here, let's say here's nanohertz, millihertz, and here's LIGO, right, 10 to the 2 hertz. And the kind of the type of spectrum that you get is typically like this, a small peak here, and then roughly constant going up to very high frequencies. And there's really only one model parameter, which is the energy scale, right? So this V squared, that would like essentially do the height of this Mexican hat here, parameterized by mu. So typically people write this in terms of G times mu, where G is a Newton's constant. And so if you lower the energy density, you lower these curves and you move them a bit to the right, because you're moving essentially to earlier times. So the bump here, I mean, the flat spectrum here comes again from radiation domination. In some sense, this is similar to what we saw for inflation. And the bump here comes essentially from some sensitivity to the matter-dominated era.
Get sharper then.
And now, just to give you some comparison, where are current experiments, right? So I haven't given you any numbers here, but like if we draw LIGO will be about here. And this G mu value here will be roughly something like 10 to the minus 7 or so, which translates to an energy scale, to a scale of V, pretty much around the grand unification scale, right? So here you would get V roughly 10 to the 15 GeV. And any higher energy scales, so any phase transition which forms cosmic strings at an energy higher than 10 to the 15 GeV is excluded by the LIGO bound. And that's actually a pretty serious constraint. And it's also interesting because here we're probing these energy scales from the top, right? Whereas colliders always probe them from the bottom. So we're really putting a bound from the top on the energy scales that these type of phase transitions can happen. Then we also have these pulsar timing arrays. So pulsar timing arrays are at nanohertz. Oops, I can also say a bit more about them if you want. But so here, if you just sketch these constraints, I don't know, they would be like this. So they are very strong. So they actually constrain, if we continue this line like this, right? They would constrain G mu values down to 10 to the minus 11, right? And remember that mu goes as a V squared, right? So this is an even more serious constraint coming from the top on the energy scale of these phase transitions. And then if we get LISA, space-based interferometer, who could really cut in here in this region in between and can kind of also probe these energies here. It's actually, so yeah, I drew it correctly. So LISA is more sensitive than the current pulsar timing arrays in terms of this G mu parameter. And yeah, so as I said, this bump here is gravitational waves emitted in matter era, and this flat part is in the radiation era. And the reason it is flat is kind of very similar to why it is flat during inflation, right? Is because the source is the scaling property, so the source is somewhat scale invariant, and then it's a question of multiplying it with a transfer function, and transfer function during radiation domination is flat. So we can conclude from this that, interestingly, large symmetry breaking scales are excluded. So again, this is the opposite direction than usual collider bounds would go.
So the pulsar timing array bounds, okay, depends a bit, but roughly you get that G mu should be smaller than 10 to minus 10. So I did it wrong here, should be 10 to minus 10. And that corresponds roughly to an energy scale of 10 to the 14 GeV, roughly. So this is really a serious constraint on models of grand unified theories, because they really want to kind of live at energy scales even a bit higher than this. So this is complementary to collider searches. It's a probe of grand unified theories. And I should mention, this is kind of really some, so this is kind of the standard story. In this way, it has been known for a while. I wanted to mention that kind of one thing that I and my collaborators have been working on very recently is that a point that had been overlooked is that these, in these grand unified theories, you may have not only, you may have multiple phase transitions. One of the phase transitions lead to the cosmic strings, but you could have another phase transition which allows you to form these one-dimensional topological defects, so which allows you to form monopoles. And this is essentially, this is a question of kind of the exact nature of, it's only a question of the symmetry group that you have, right? So the grand unified theory means you take the standard model, you want to embed it in some bigger group. And now depending on the exact structure of that group, it may be possible to have also monopoles in your theory. And these monopoles would be Schringer pair produced along these strings. So it's simply, it's an exponentially suppressed process. It's very similar to, say, the generation of electrons or positrons in a strong electric field, right? If you have a strong energy in the background, you can, in kind of the vacuum, you can form vacuum loops of electrons and positrons, and then the electric field will tear them apart, right? So that you actually form physical particles. And the same process happens here. But once you form these monopoles on these strings can decay. So that means they are no longer topologically stable, and they may have a lifetime which is shorter. It's still pretty long, but it may be shorter than the life of the universe. And then what would happen to these curves is that they would simply kind of be cut off at some energy, at some frequency scale. So it would stay the same at high frequency because this corresponds to early times. But then essentially the low frequency part will be cut off, which means that you kind of a null detection at these pulsar timing arrays could be perfectly compatible with a strong signal at LIGO that we could see whatever tomorrow, right? So this is just to say that really, despite that kind of in the naive story, the pulsar timing bounds kind of tell us that LIGO has poor chances of seeing anything. In fact, once you take this effect into account, really kind of every inch that LIGO moves down on this plot is really putting serious constraints on, I think, very, very reasonable models as kind of in the, well, in the way that BSM models are reasonable. Yeah, so this is kind of, so this is I don't know, how should I say, this is kind of the result that you get if you include monopole production. I don't really want to go into all the details, but I just wanted to tell you that yeah, there is this kind of recent development, and this is really kind of very promising for the prospects of LIGO to see such a thing. Okay, do we have any more questions at this point? Yes, Gautam.
Yes.
Yeah, I mean, it might probably be a silly question. So as you lower the energy scale for this graph, would the peak keep getting sharper because you're moving further and further back in time, or would it still have a decent amount of smoothness?
No, it's really just a shift of the, it's just a shift. So what essentially happens is that as you lower G mu, what happens is that the rate at which you emit gravitational waves decreases, which means that essentially your network kind of undergoes the evolution in a slower way.
And that means kind of from the point of view of the intrinsic time of the network, the point in time when matter domination becomes important happens earlier or later. And this is kind of why this is shifted in frequency space.
I see. Okay. Thank you.
Any more questions?
Yes.
Hi, I would like to do a question about gravitational waves in first order electroweak phase transitions. Which are the chances that we can distinguish between models when we measure a gravitational wave signal corresponding to a phase transition?
Yeah, very good question. So what we would hope to, it all depends on the amplitude, right? So it depends on how well we can resolve things, right? So if we have, so let's say this is omega f, right? And let's say this is, for example, our nice LISA sensitivity curve, right? And if we now have a signal which is really kind of nice and loud in the LISA band like this, meaning a very high signal to noise ratio, then we expect that we will be able to reconstruct the signal very well, right? So we will essentially really kind of run our codes, right? And then we will really kind of see, aha, there's really a peak like this. And we will know it, of course, there would be some uncertainty band, right? But we will know it pretty well. Mm-hmm. And if that is the case, and then we will know the peak here, right? The peak frequency, the peak amplitude, we will know the slope here and the slope there. And if you have all this information, then you can really already learn a lot, right? So from what I told you beforehand, you can see that the peak frequency, right, is directly related to the temperature at which this phase transition happened. And the amplitude is directly related to essentially how much first order the transition was. So what is the amount of energy that is released when going from the false vacuum to the true vacuum? And then the slope here would kind of tell you what of the different contributions like turbulence, sound waves, and so on, what is the dominant contribution? So if you had all of that, you could really nail it down pretty well. Of course, it will always, I think, be the case in the nature of humans that as soon as we have a signal, right, the archive will explode, and there will be a lot more than one paper which claims to explain it. But at least kind of at the kind of thermodynamic level, I think you could extract the parameters, right? Then the question is like, what microphysics is responsible for changing the Higgs potential in this particular way, right? This is a different story, right? Then there's clearly more degeneracies. Now, we might, however, also find ourselves in a situation that we only kind of have a very small signal, right? I mean, it can still be like big in this, right? So it's even underneath the sensitivity curve, right? And then we may even, or maybe kind of just barely touching the sensitivity curve. And then we may even have, in addition to complicate things, we may have an astrophysical contribution from the black hole mergers, which is maybe even bigger, right? So then we're looking for a teeny bump, right, on top of this power law. And that is a much more challenging question, right? And then at most, we will be able to extract the frequency and the peak amplitude, right? But we will not be able to extract anything about the slopes. And then there will be much more degeneracies in explaining this.
Yeah, but aren't there very big uncertainties still, for example, in parameters like the bubble wall velocity and so on?
Yeah, but I mean, this is why I'm saying that kind of, I think the there's some chance of extracting the thermodynamic properties, right? But then when you relate those really to the microphysics, there's more uncertainties. And at the moment, also kind of we theorists have to do a bit more homework, because even if you specify the given thermodynamic properties of a model, at the moment, it's still tricky to compute the gravitational wave spectrum, and there's still kind of disagreements on what exactly is the gravitational wave spectrum, or there's still uncertainties in the calculation. So we better, by the time we have 10 more years, right, until LISA flies. And by that time, we kind of better have a better understanding of the theory prediction. Mm-hmm. Then of course, I mean, if we actually see a signal, right, I mean, if LISA sees something like this, then of course I think the funding is guaranteed to build the next mission, right? And then you will measure things with higher precision.
Okay, thank you, Valerie.
I should have done a second poll, huh? When I ask you now, what is your favorite model? Okay, so then let's just a few more minutes. I just wanted to show you some pictures for these experiments I've been talking about. I've been kind of mentioning them from time to time. But so essentially, there's three classes of experiments here, right? So the pulsar timing arrays. Here, this would be LISA and LIGO. So maybe the best known here is LIGO, right? So this is this plot down here. So this is a Michelson interferometer, right? This is one of the two LIGO instruments, and then there's also Virgo in Italy, and now also Kagra in Japan. So these are all similar instruments. So essentially, the idea is you send some laser light up here and down here. And actually, you don't only send it up and down, you send it back and forth, back and forth, back and forth in a cavity, but let's ignore the complication, and you send it like this also. And then essentially you check when these two waves arrive back. Here you have a mirror. And when these two waves arrive back, you check kind of if there's a phase difference in between the two waves, right? So you kind of measure in a very sensitive way. You measure the length of this arm with respect to the length of that arm. And the length of these arms is kilometer scale. Now, and this is the instrument that we already have. Now, kind of the extension of this instrument is LISA. So LISA is essentially the same idea, but put into space. So this is nothing that exists yet, but this is an approved ESA mission with launch date in 2030 or so. So we're pretty confident that this is going to happen. Like the funding is there, and people are working on instrumentation and all the nasty details. But so the idea is that you have 3 satellites, and these 3 satellites are exchanging again laser light, right? So the type of measurement is the same that is performed in LIGO, but the scale is different, right? So here you see the Earth, the Sun, the Moon, and these satellites. So the idea is that these satellites kind of fly on an orbit similar to Earth around the Sun. And the distance between these satellites is something like 2.5 million kilometers. Right, so it's really a completely different scale, and hence LISA is sensitive to frequencies which are much lower than LIGO, simply because the satellites are much further apart. And then it also becomes, if you look at this plot, it also becomes very clear why you cannot build such an instrument on Earth, and also why it's so difficult to build this instrument. I mean, even shooting a laser beam from one satellite to the next over this distance and then actually hitting the satellite is a non-trivial exercise, right? At the moment, the furthest that we've ever done is we've shot a laser to the moon, right? And kind of see it reflected off the moon. So we're pretty sure the moon is there. And we've been on it to put a reflecting plate there. But this is really a whole different story. And then the third class of experiments that we currently have are these pulsar timing arrays. So these are these very low frequency gravitational wave instruments. And here, again, the idea is similar, but now it's even much bigger distances. So now you use the fact that you have naturally in the universe, you have pulsars. So pulsars are neutron stars, this guy, for example, which are rotating and emitting essentially here a light beam in a particular direction. And now kind of as this thing rotates, eventually kind of the light beam will point in the direction of the Earth, and we will see a flash. And these guys rotate in milliseconds, roughly. That's the orbital period. And so when we observe them, we see very regular millisecond flashes coming from these objects. I mean, in theory, they're very regular. In practice, turns out they're not. That actually, there's a lot of nasty astrophysics going on, right? But kind of the spacing is very regular because the spacing is really just the rotation period of that neutron star, and that's not changing much. And also the idea is that if a gravitational wave passes between you and a pulsar, then you will have a distortion in the arrival time of these signals. Now, there's many things that can cause such a distortion, right? So for example, whatever, some planetary object or something, you know, some asteroid, you know, flies close to your path of light, you will have some lensing effect, right? And you will also kind of see this as a distortion in the arrival time. So in order to be sure that it's gravitational wave, what you need to do is you need to actually look at not a one pulsar, but you need to look at many, many pulsars. And you need to make sure that kind of the distortion signal that you see from all these different pulsars is compatible with the hypothesis that it's a gravitational wave, right? So there's some correlated distortions of all these timing signals, and that's what you're looking for. And this type of experiment has been going on for a very long time. We have data on observing pulsars which goes back 40 years or so. And very recently, last summer, actually one of these pulsar timing array collaborations, the nanograph collaboration, actually put out a paper where they said, okay, we see a stochastic signal. We see that it's correlated across all pulsars. They don't yet have the statistics to see if the shape of this correlation is really compatible with gravitational waves, or if maybe it's some instrument systematics, I guess, would be the leading or the alternative. But yeah, so this is something which is really happening now, and there's also other collaborations which have a similar amount of data, and which will also be putting out results very soon. So this is at the moment my bet would be that the first detection of this gravitational background comes from the pulsar timing arrays, in which case it would the most likely origin would be very, very heavy supermassive black holes. And the unresolved parts of these black hole mergers is what could create a signal in these pulsar timing arrays. But of course, right, as you see from this plot, you know, it could also be cosmic strings, of course. That is always a possibility. Okay, so I think that's all I wanted to say. So I'm happy to take any more questions.
Thank you very much, Lily.
I would also ask you to do the last poll, right? So here's the link again, in case somebody missed it. So one last poll, just giving me some feedback on the lectures. But yeah, I'm very happy to take any more questions.
Everybody is Niklas.
Let's see. All right, am I audible?
Yes.
Oh, sweet. So my question regards if, let's say you would have some additional